Okay, so as we were saying, one way looking at this, the temperature is going to go up because there's work coming in, there's no heat or work coming out, so therefore the temperature will have to climb. That's basically the first law of thermodynamics, which we'll be getting into more in depth in this later in this chapter. The other way of looking at it is that, if you're familiar with refrigerators, the temperature, um, in here definitely the temperature goes down in the ice box and more in the ice box than in the actual refrigerator part. So this is associated with low temperature. So I'm just going to say like let's say TL, this blue color. But we know that there's heat rejection. If you hear any rustling in the back, I apologize. That's basically my headset. I'm doing this lecture outside because it's nice. In the back of the refrigerator, there's coils. And so I'm kind of depicting the back of the refrigerator. Sometimes they're at the back or sometimes they're at the bottom, depending on the refrigerator. But here is where heat gets expelled. So we're going to call this temperature hot. So if you really think about it, the way we get the heat out is basically to throw it out the backside. But we're going to find out later that because there is no 100% energy conversion, right, because of frictions and machines not being 100% efficient, we're going to have more heat getting rejected out the backside than we have heat basically being drawn into the end or removed from the inside. So in order to get this refrigerator cold, we have to get that heat, throw it out the back. Plus, we need to throw out the heat that we're generating by actually running motors and doing any work, because there's, again, due to frictional forces and other conditions, we are going to basically generate more waste heat than we are heat drop, if you want, for sake of a better word. That's another way of looking at it. And if there's a net amount of heat, high heat or heat loss that stays in the room and isn't able to come out through the walls, and therefore it's going to raise the temperature. But again, if you just look at this as boundary conditions and you look at there's something going into this green dotted line, there's nothing coming out, then temperature will go up. Okay, so let me do a new page here. All right, so next topic we're gonna in the topic is still forms of energy. So let me go back to the pen here. Forms of energy. So what we like to do here is all energy. We want to give it the letter E, right? The capital E is a total form of energy. Sorry, physical total energy. Total energy. And if we want to divide by unit mass, we give it the lowercase letter. So it's basically capital E divided by mass. And so what I forgot to mention is up here, the units would typically, for our SI units, we're going to be in kilojoules or joules. But because of the large amounts of heat that we'll be tracking, it's better just to use kilojoules. And here, since we're divided by unit mass, we say kilojoules per kilogram. Now this is the preferred form of energy, or at least representation is the lowercase, because now we can solve any problem from very simple, small to very large scale, and we solve it per unit mass. So mass isn't a factor. And then at the very end, we'll just multiply by the mass of the system. And then we get what energy that we, whatever the question is asking. So we prefer the lowercase method here to divide by unit mass. And so there is, for thermal, in the study of thermodynamics, we don't really talk in absolute terms. Let me see. no absolute terms, and I'll explain what that means. But what no absolute terms means is that we don't say this system has so much energy, or that quantity of mass has so much energy. Uh, so that would be absolute. We're looking at energy change. So we're looking at changes of energy, and for that, um, we need at least 2 points of data. So I'm going to say 2 data points. Two data points needed, and um, so therefore something like a before and after, followed by an after. That's kind of what we're looking at here in thermodynamics. So we never say that we don't have a quantity of, so say this big rock here, and it has a certain quantity of energy, you know, that we don't say this block has a certain quantity of energy, right? Absolute, and then head on out, because we're not in this thermodynamics. We're not in the business of saying unless we have something to compare it to. So therefore, we don't speak in these terms. We need 2 data points. All right. So typically we have there's different types of energy forms. There's macroscopic, and the macroscopic has to do with potential energy, kinetic energy, etc. So this is, if you just think of large scale uh, energy sources, so things that happen on the outside, so they happen on the outside of a system, typically. Then we can also look at microscopic forms. Microscopic. And for that, we basically strictly say we label it U, and that's internal energy. So that's something intrinsic inside, relative to a certain quantity of material. Do a new page here. All right, so for example, we mentioned about kinetic energy. Kinetic energy is what we call Ke, and we know that the measurement of Ke typically in a system is the mass times velocity squared divided by 2. And that'll give us units of kilojoules. And then we know potential energy is mass times gravity times the height, z, and that's also in kilojoules. And we know if we use the lowercase letters here, Ke, little k, little e, we divide by mass. So this is going to be per unit mass. So it actually simplifies a little bit by just giving us velocity squared divided by 2. And that would be the units for that. We just have to make sure we don't forget about our mass at the bottom, kilograms. And again, little p, little e is equal to just g, c, with the same units, kilojoules per kilogram. So if we were talking as far as total energy would encompass everything we talked about right now. So a system may have all forms of this energy. So we would have the internal energy, and then we may have some kinetic energy, and then a quantity of potential energy, and then since we're talking total energy, not per unit mass. And of course, if we're talking about per unit mass, that would be little u plus little ke plus little pe kilojoules per kilogram. So just know in general, when we letter, that means per unit mass. Okay, so now we're going to talk about closed systems. So the example I gave earlier about the refrigerator, that is a closed system. So a closed system, it has to do with, so we had a box, and then we had basically, we're defining a control boundary as the inside of that box. So that would be a closed system. And in a closed system, nothing gets in, nothing gets out, no mass gets in. So in terms of coming in and coming out of mass, for a closed system, again, we assume that no mass gets in or out. Maybe I should just color this all red. So no mass gets in and out. That's the definition of a closed system. If we allowed mass to come in and out, for example, a water flow, a stream coming in, if we assume any kind of mass flow rate, then this would be an open system. But this is the definition of a closed system. So open systems typically deal with let's see, open systems, which we will get more into depth with these, like in chapter 5. These have to do with mass flow and mass flow rates of typically a liquid coming in and out, and typically that would be defined as m dot, and that would be an example to calculate. That would be density times volume flow rate, which I like to give that designation, and that would give us units of kilograms per second. So flow rate would be, a volume flow rate would be liters per second or meters cubed per second, and density would be kilograms per meter cubed, right? So then your end result would be a kilograms per second. Okay, let's go on to our next page here. So now we're going to discuss, oh, and I forgot to mention energy flow rate. Energy flow rate. So we talked about energy. So if we put a little dot, that means it's the energy. We have units of kilojoules. This would be like a kilojoules per second. So the way we could write this would be to do a mass flow rate times an energy per unit mass. And so for this, the units would be would give us something like kilojoules per second, or we call that kilowatts, because a joule per second is a watt. So again, the energy flow rate, we're talking about energy, total energy is kilojoules. When we attach a mass flow rate, so if you remember, the lowercase e is kilojoules per kilogram, we multiply it by kilograms per second, we get a unit of kilojoules per second, which is a kilowatt. So we're going to be using a lot of energy flow rates here as well. And so now let's talk about some physical insights. Some physical insights. The first one is sensible energy. So what is sensible energy? Sensible energy is the energy that we feel when we touch something that's cold or hot. And the reason when we touch something that has a high temperature, it's because, well, there's, matter is composed of atoms, right? And so atoms move, and so they have. So this would be a molecule, and it's going to move, right? So this would be transit. And when they move, they have a certain amount of energy, and they can also rotate. So molecules can, for example, atoms bonded to each other forming a molecule can rotate, and then they could also vibrate. So if you had an atom here, and we do kind of it's bonded to another atom, the bonds act like a spring, and so this could be, just this bond will be vibrating, so it would be molecular vibration. All this translates into forming higher temperatures or producing heat that we sense. So I'll just say that we sense, right? We can actually touch it, put our hand here, and just drawing a hand here. Sorry for my bad hand here, but we can actually touch this, and we can feel the effects of all these different types of molecular vibration and rotations and transit. The that's one form of energy. The other is latent, and this is actually an area that I like a lot. It has to do with phase change. So it turns out that for pure elements, and we'll talk that more in the next chapter. Elements, for example, doesn't have so it could be water, um, oxygen, any type of element that typically you can go from a solid to a liquid to a vapor. These are phases, and it turns out that when materials go from a solid to a liquid, then they actually when they go from so let's look at it this way. When you're going from a solid to a liquid, you're actually releasing energy and in the form of heat. And then when you go from a liquid to the vapor phase, you also are releasing energy in the form of heat. Actually, this one, you're either absorbing or releasing. This time I have this one backwards here. But in order to go from liquid to vapor, you need to put in a certain amount of energy to make the molecules basically go from liquid molecules to vapor molecules. And so it absorbs energy, and we use this in many applications in engineering. We'll discuss those later, but that form of energy is latent energy, or sometimes we call it latent heat, and it's very powerful. It's a very powerful way of removing or absorbing large quantities of heat, larger than sensible heat, because this this phase transition requires a lot more energy than for a unit mass than sensible energy does for a given temperature. Okay, now we're gonna go ahead and change the page here. Darken this black here. All right, so now we're going to talk about mechanical energy. I'll just say mechanical E to save time. Mechanical E, we did mention forms of mechanical E. We did mention potential energy, kinetic energy. Also, fluid flow has energy. Has anyone that's ever had a water hose and you spray a box or something and you can knock it over, um, or any type of, have you ever done a bottle rocket, a water bottle rocket, where the pressurized water shoots out the back of a bottle and it launches your, so it's fluid flow is a form of mechanical energy. We like to say EMEC, like that, and typically that is for fluid energy, that's pressure divided by density. For kinetic energy, per unit mass, again, we're doing the lowercase e here, velocity square divided by 2, and for potential, it's gravity times height. Okay, and if we're, because we don't talk in absolute terms, we talk about changes of energy. For changes of energy, you need at least 2 data points or 2 states. And so we would have not just 1 pressure, but 2 pressure. So we'd be looking at a pressure difference divided by the density plus a kinetic energy difference between 2 velocities. And same likewise, a potential energy difference between 2 different heights. And if these are in terms of per unit mass, so the units for this would be kilojoules per kilogram. To get the total energy, total E, or for example, what if we're talking about an energy rate? Then we need to multiply by the mass. But because we're talking about rates here, we need a mass rate or a mass flow rate. And we can multiply that by little EMEC or lowercase EMEC, because this is a per unit mass. The units here are kilojoules per kilogram. So then this would give us mass flow rate, again, times everything we just mentioned up there. I won't, it's basically P2 minus P1 over density plus the differences in the velocity squared plus G times the difference in the height, Z2 minus Z1. Oops, Z1. Okay, you get the idea? Very good. Let's continue. All right, so we're going to do an example. We're going to do a wind energy example because we are very sensitive to sustainable energy, typically, these days. And we're going to see what kind of energy can we generate from the wind. Again, we can't create or destroy energy. That would violate the first law of thermodynamics, but we can convert it. So how much energy can we convert? Let's get a good idea from a windmill. So let's suppose we have a velocity here of the wind, and it's equal to 8.5 meters per second. And it's going to go across our blades here of our large turbine installation. So we want to find so we want A to find the energy per unit mass. B, we want to find the total energy. And C, we want to find the energy rate. Okay, so the first thing is we want to find, again, we want to find the energy per unit mass. And we know that when we're talking in terms of this turbine here, we're talking about the wind going through the turbines and causing this thing to rotate, right? So this thing will start rotating in whichever direction it's designed to rotate due to the velocity of the wind. So this is strictly a kinetic energy device. So we're not looking at the wind changing height differences and and that kind of thing. This is strictly kinetic energy. So we're going to say KE, and that per unit mass is V squared divided by 2, which is 8.5 meters per second squared divided by 2, which is equal to 36.1 meters squared per second squared. We're not done yet. It turns out that these unit meters squared per second square, so it turns out that 1 meter squared per second squared is equal to 1 joule per kilogram. So maybe you can do that off on the side. See, assure yourself that that this calculation, that a meter squared per second squared, if you can do the unit conversion, will give us a joule per kilogram. Maybe that's something you guys can do on the side there. But that's basically our conversion. So therefore, this is equal to 36.1 joules per kilogram. Very good. So that satisfies A. Now for B, we're looking for total energy. So for total energy, we just have to multiply the mass times the energy per unit mass. And one thing I'm not sure if I didn't give you up here at the top. Turns out that we want to, the mass, this was given in the problem, but I didn't mention out here. The mass of the air given at we wanted to calculate for 10 kilograms of air mass. So this would mean we would get the 10 kilograms, and we'd multiply by the energy per unit mass, which would be 36.1 joules per kilogram. And then the kilograms cancel, and we're left with 36.1 joules. I'm sorry, did I say 10? Yeah, it's no, I'm sorry. It's 10. I'm sorry. So it's 361, which basically is equal to 0.361 kilojoules. Good. And now to satisfy C, we're looking at energy flow rate. And one thing I neglected to mention is in the problem they give us a energy flow rate to make our calculation of 1,154 kilograms per second. So these were given. I didn't write them up ahead of time. But if that's the case, then we know that E dot is equal to M dot times little e, right, which is equal to 1154 kilograms per second times 36.1 joules per kilogram. We know the kilograms cancel out, we're left with joules per second. And so we're left with an answer of 41.7 kilowatts. So 41.7 kilowatts. So this turbine that we didn't really specify dimension has the ability for wind speeds of 8.5, roughly, if I had to guess, is that like 16? You know, they're decent winds, 16 miles per hour type of wind, almost a little bit less than double this. We can generate 41.7 kilowatts. That's typically, you need about 4 kilowatts or so to power a small home. So we can power a little over 10 homes with this turbine. Okay.